Hello everybody. Today we're going to begin looking at section 3 of chapter 3. This is where we're going to look at different situations where we can use Newton's laws for everyday events, okay? So our main idea here is that Newton's laws can be used to explain everyday events such as falling, collisions, circular motion, and other similar events. Oops, I'm sorry, I didn't realize y'all couldn't see that. I apologize. So there it is. Take a moment to write that down. Newton's laws can be used to explain everyday events such as falling, collisions, circular motion. We will be looking at some of all three, okay? The first thing we're going to do is look at what happens in a car crash. Now, just recently, for extra credit, you watched a video on understanding car crashes. Pretty cool, huh? Watching them all crash. I like the slow motion ones where they show what the dummy does. In a car crash, the stopping force acts on the car to decelerate it to a stop. Now, you might think that if you were not wearing your seatbelt, that all you would have to do is put your hands on the dashboard and keep yourself from going forward. Well, let's think about that a minute. If the car was initially traveling at a speed of 50 miles an hour, just 50, that's not even really interstate speed, is it? Because most of us travel 70 or more on the interstate. Let's suppose you collide head-on with something solid, either another car or maybe with a bridge abutment or a tree, something like that. Well, the car will crumple, which decelerates the car to a stop. And it'll do this in about a tenth of a second, just a tenth of a second. According to Newton's first law of motion, the passengers in the car will continue moving forward because of their inertia at a speed of 50 miles an hour, because that's how fast the car and you were going, until a stopping force, like going through the windshield and hitting the ground, stops you, okay? Now, this means that 0.02 seconds, 0.02 2/100ths of a second, after the car stops, any unbelted or unrestrained, that should say unrestrained, oops, typo, passengers will strike the windshield at 50 miles an hour. So what would that be like? Could you stop yourself from hitting the windshield at 50 miles an hour? Well, think about this. Let's suppose you stepped off the 5th floor of a tall building. Falling off from the 5th floor, you would hit the ground at about 50 miles an hour. Do you think you could hold your arms out and keep yourself from hitting the ground as hard? Nope, you couldn't. Neither could you do the same if you were in a car crash. What would happen in either case, falling or the car crash at 50 miles an hour, you would shatter the bones in your arms. Yep. That's exactly what would happen. You would shatter the bones in your arms. So this is one of the reasons we wear seat belts and we have airbags in our cars. Both of these are to transfer braking force or stopping force from the car to our bodies so that we slow down with the car, and hopefully it prevents us from obtaining serious injuries. When the engineers develop cars, they're always thinking of ways to make cars safer, and they work on developing new ways to keep us safe, such as improving crumple zones. Now, it used to be cars didn't have crumple zones. In fact, cars used to be made with thick steel metal, and it didn't crumple very much at all in a car crash. That's why a lot of your older big cars, you hit them even just a little bit, nothing happens. The big car, nothing happens to it. It looks the same. It didn't even get its dent, and your car is all crumpled up, okay? Because they didn't have crumple zones built into those cars. But there's also a problem with that. Without a crumple zone to absorb the energy, because that's what a crumple zone does, it absorbs energy of the crash. I wrote that down wrong right there because I was saying the word cars at the same time. Sorry. Okay, crumple zones. All right, crumple zones absorb the energy. And when it absorbs the energy, this means it increases the time it takes the car and you to stop. And if it increases the time to stop, it decreases the force that's exerted on you. Okay, this is one of the things they talked about in the video on yesterday or on Monday for the extra credit. If you remember the 2 eggs that were thrown by the teacher, he threw one at a wall and he threw one at a sheet. The one that hit the wall burst into all over the place, just egg goo everywhere, right? But the one that hit the sheet that was hanging there, it didn't break at all. Now, why is that? Well, the sheet had more give. So basically, it slowed the egg down over a much longer time to 0. So it didn't take as much force. But the egg that hit the wall, it slowed down in a fraction of a second. To do that, it took a much larger force, a force which broke the egg. So crumple zones absorb the energy by increasing the time it takes to come to a stop, and therefore it decreases the stopping force that acts on you and could cause you serious injury. We don't want that. So we want to decrease the stopping force that acts on you in a car crash. So they improve crumple zones so that they crumple more and keep you safe. Now, another safety feature is the safety cage. The safety cage is basically the passenger compartment, okay? The safety cage. This is the compartment containing the passengers where they sit. Engineers try to design a safety cage that will not have any intrusion into it during the crash, because intrusions into the safety cage obviously could cause major damage to the people sitting inside. So we don't want the engine pushed back into the safety cage, do we? No. So we try to make sure that the safety cage is strong and can protect the passengers. Okay, so Newton's first law deals with all this. We know that if your body is moving with the same speed as the car and the car is involved in a crash, your inertia, according to Newton's first law, wants you to keep going forward. So to keep that from happening, we wear seat belts and we have airbags to protect us. And that will allow the transfer of the braking force or stopping force to be transferred to us and slow us down with the car so that we don't go through the windshield. And that's from Newton's first law. A body in motion wants to stay in that motion. So if you're traveling 50 miles an hour with the car, your body wants to continue going forward when the car crashes. So wear a seatbelt always. All right. Gravity revisited. Let's talk about gravity in Newton's laws again. Now, in the first section, we talked about what gravity is and how it can be calculated. And so what we want to do is revisit some specific phenomenon associated with gravity. One of them is the idea of free fall. Now, we mentioned this in section 1 of this chapter, but I want to go over it again so that you remember. Free fall is what happens to an object when the only force acting on that object is gravity. Under those conditions, when the only force acting on an object is gravity, which points straight down towards the center of the earth, then that force will cause the object to accelerate towards the center of the earth. We say the object is in free fall when that happens, okay? Now, how do we know what acceleration it will have in free fall? Well, it depends on the planet. Remember, we said that there's two ways to find the gravity acting on an object from a planet. The first way, which is a short way, is if you already know the acceleration due to gravity that the mass of the object, O for object, would have on that planet. If you know the acceleration due to gravity, you multiply by the mass, you get the gravity. But Newton also said, well, sometimes you don't know the acceleration. So what do you do in that case? So he determined that you can use this formula, which is a proportionality constant times the mass of the object times the mass of the planet that you're on divided by the distance between you and the planet squared. And by distance, I mean from the center of the planet to you, okay? If both of these are accurate ways of determining the gravity or weight of the object, hang on just a minute. Okay, these two methods, since they represent the same thing, we can set those equal to each other. So we get the mass of the object times the acceleration due to gravity, if you know it, or if you don't, you can say this proportionality constant times the mass of the object times the mass of the planet divided by the distance between them squared. Now your algebra teacher would say, oh look, you've got the mass on this side, you've got the mass of the object on that side. Since it's on both sides, if you divide both sides by m sub o, it cancels out. So what does that leave? That leaves the acceleration due to gravity on this side equals, oh look, the mass of the planet divided by the distance squared. So this means that the acceleration due to gravity depends only on the mass of the planet and how far you are from its center. We always measure from the center of the planet, okay? So, it doesn't depend on the mass of the falling object at all. So why would a golf ball and a bowling ball, oh actually I think I said marble right here. So why would a marble and a bowling ball hit the ground at the same time? Because their accelerations on a given planet does not depend on their own mass, but the mass of the planet they're on. So if you drop a marble and a bowling ball at the same time from the same height, they will hit the ground at the same time. They will do it. In fact, Galileo proved this by taking two similar objects but had very different masses. One was heavy, one was not so heavy. He took them to the top of the Leaning Tower of Pisa. Of course, he was on the side that kind of leaned over, all right? And he dropped them both from top of the tower. In fact, if you don't know what the Leaning Tower of Pisa is, the Leaning Tower of Pisa is a bell tower for the church right next to it. Okay, so he went to the top of this bell tower, which we now call the Leaning Tower, and he dropped it, both of them, at the same time from the same height, and lo and behold, they hit the ground at the same time because the mass of the two objects has nothing to do with the acceleration that the Earth produces for them. When the Earth pulls on them, it gives them each the same acceleration. Yes, one may have more mass, but because it has more mass, the Earth exerts more force on it to give it the same acceleration as the lighter object. How about that? Okay? All right. Now, so that's a marble and a bowling ball, but what if we change the situation a little? What if we drop a marble and a feather at the same time from the same height? Like right here. Here's a feather, here's a marble. Suppose we drop them at the same time from the same height. Well, I think you know what would happen. I think you know that the marble will hit the ground first. And the feather after, at some point. You know what feathers are like. You've seen feathers. The feather later. Okay? So, a feather, instead of falling straight down like a marble will, a feather kind of wafts its way down, doesn't it? Okay? It doesn't fall straight down. Now, why do you think this happens? Well, it happens because of air resistance. You see, on Earth, we have an atmosphere, thank goodness, because we need to breathe in order to live. But that atmosphere produces air resistance. Air resistance is simply friction between the air and an object moving through the air, and it always acts opposite the direction of motion, and it increases with increased speed. So, as the feather falls, it's dynamically made so that it will waft around. All the little fronds on the feather will catch the air molecules, and that air resistance will make it waft around. But the marble is spherical, which is fairly aerodynamic. So it just pushes those molecules aside and goes straight down. Okay? So air resistance does affect things. Now, what if we took our feather and marble to the moon? Now, the moon is a smaller planet, so it doesn't have as much gravity as Earth, but it doesn't have an atmosphere, does it? So on the moon, with a vacuum, with no air resistance, guess what? The feather and the marble will hit the ground at the same time with the same speed. Unlike when you have air. This one wafts around and takes longer. This one goes straight down rather quickly. But on the moon with no vacuum and with no air resistance, they hit the ground at the same time. And later on, after spring break, I'm going to prove it to you. I'm going to show you a video of what happened on the moon, on one of the moon shots. It's pretty cool. It's history too, which is neat. Okay, that is basically, we got to go over this a little bit. Sorry. Okay, so here's how it works, all right? Here's how it works. I tell you what, you know what? Let's save that. Let's save that for tomorrow when we go over that, because I think it'll be more interesting for you tomorrow. So I want you to kind of digest this a little bit. Think about what we said. Tomorrow, we're going to look at how that works, okay? What forces are actually involved? How is Newton's second law involved in a marble falling versus a feather falling, okay? All right, so I'll talk to y'all tomorrow. Bye-bye.